should be recording. Are we still recording? I hope so. Yes, we are recording, so that's good. And now let's go over to screen share, and we go into this one here. It doesn't matter. So right now, let's hope for the best. Can you see the screen? With Excel on it? No? No, it's black. Oi, 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 oi. Let me see. Okay, book 1 Excel. Now, can you see it now? Ah, okay, screen is back. So, BI301. Can you see what I'm writing? BI301. Can you see BI301? Cool. So what we are going to do today is inhibitors, and the good thing is we haven't missed too much. So we are back in business. Okay, excellent. So let's quickly recap what we have done before. We said Vmax, that is the enzyme parameter that tells us how the enzyme behaves when the substrate concentration is extremely high, like that. Okay, what about Vmax over Km? What does that tell us? How the enzyme behaves, Vmax over Km, is extremely low, exactly. So when the substrate concentration is extremely low, that's absolutely right. And we have Km, and that tells us the affinity of the enzyme, how much the enzyme actually likes the substrate. So if Km is low, then we have a high affinity. The enzyme really likes the substrate, high affinity. So that's what we have here. So Km is low, low Km, high affinity, and the other way around, high Km, low affinity. So this is all good. We also did my favorite plot. We discussed that, where you plot V over S versus V, and we would get sort of a straight line. The gradient of this straight line gives us negative Km. The y-intercept gives us Vmax, and Vmax over Km is this point here. Okay. So Km tells us the affinity, and this means if Km is low, then we have high affinity. If we get a low affinity, if Km...
No, we're just discussing something else right now.
What are you doing now?
Yeah.
Do your head
relationship, it's inversely related. Exactly. Okay, so that is where we stopped more or less the last time. And just for completion, this kind of plot is called an Eddy Hofstee plot. It's not Eddy the Eagle plot. I got that in some exams. Okay, so what we are going to do today is we are talking about inhibitors. So first of all, we need to distinguish between two different forms of inhibitors. So inhibitors come in two different flavors. Does anyone know which flavors they come in? What kind of inhibitors? Vernon, wonderful, because I expected this answer. Absolutely brilliant. And what you are offering me are subclasses of one of these two flavors. And with delight, I see that a lot of people go for non-competitive. But Ellie, I love that, reversible and irreversible inhibitors. So we can have irreversible inhibitors, and these are actually the classes that I'm talking about, irreversible, and we can have reversible inhibitors. So these are the two main classes. Irreversible inhibitors, these are things that, as the name says, they just are totally irreversible. Basically, you cannot reverse the action of an irreversible inhibitor. This is pretty much, it does what it says on the tin. And very often, an irreversible inhibitor will destroy the activity of an enzyme. Can you think of very simple irreversible inhibitors? Cyanide? Yeah, cyanide could be an irreversible inhibitor. High temperature, yes, absolutely. High temperature would be an irreversible inhibitor of enzymes. Or high pH. If the enzyme cannot recover from this treatment, the activity is destroyed and the enzyme is irreversibly damaged. They can be incredibly they can be very, very potent, of course, but they're not terribly interesting. So what we are now dealing with mostly, or for the rest of at least this lecture today, is we are looking at reversible inhibitors. And let's go for a very simple case of a particular reversible inhibitor. And if you take notes, leave a little bit of space here, because there's some stuff coming. So, reversible inhibitor. The first inhibitor that I want to discuss with you is a very simple one. Let's just simply write down our scheme. Enzyme plus substrate gives us this scheme. We form an enzyme substrate complex, and then we also form, for our Michaelis-Menten equation, we form product plus enzyme. Okay? This is really familiar to you, and that's not a particularly new thing. But now we introduce an inhibitor. And the first inhibitor that I want to introduce to you interacts, where do I put this? Interacts exclusively with the free enzyme. So this particular inhibitor only works on the free enzyme. And when we talk about inhibitors, we are only looking at inhibitors that do something to the enzyme. We totally discount any inhibitors that would work with a substrate or with a product. That's not something that we are interested in. We are only interested in inhibitors that interact with the enzyme. So what we can do is we can say, well, we have an inhibitor, and I write it like I for inhibitor. And in this case, I add a little C here at the bottom. I'm not saying that all inhibitors do that, because let's wait. So we have an inhibitor, and this inhibitor interacts exclusively with the free enzyme. And because it is a reversible inhibitor, I write something like that here. Enzyme and inhibitor, and they form an enzyme inhibitor complex. Okay? Are you happy with that, the way I've written it? Okay, I don't hear any dissent, so I assume that people are quite familiar with that. So let's look at what this inhibitor actually does. Let's look at the properties of this inhibitor. As I said, it interacts exclusively with the free enzyme. Only the free enzyme can interact. This one here. And I really emphasize that. If you look at this scheme, what you see is that the inhibitor IC, this is only for the reversible one. IC and substrate are basically mutually exclusive. What does that mean? Either the inhibitor binds, either IC binds, or substrate binds. They cannot bind at the same time. This is what it means, mutually exclusive. Mutually exclusive. Either the inhibitor or the substrate can bind. So they are basically both competing for the enzyme. How do I write this? The inhibitor and the substrate compete for the enzyme. Compete for binding to the enzyme. Okay? And as I said, we are talking only about reversible inhibitors. So They compete for binding to the enzyme. So the enzyme can go either this way or it can go this way, right? So what is going to happen here? How does this inhibitor affect things? Because it competes with the substrate, this inhibitor is called a competitive inhibitor. Competitive inhibitor. We come back to that. Park that question, Ella. Park that question. It will be answered in a few minutes. This is the competitive inhibitor, and it is mutually exclusive with the substrate. So, what would happen now if we had lots and lots of substrate? In this scheme, we have loads and loads and loads of substrate and only a little bit of the inhibitor. Which one would predominantly bind? Substrate or inhibitor? If we had loads of substrate. Absolutely right. We would see predominantly the substrate bound. So, with lots of substrate, the substrate would outcompete, and Imogen is absolutely right, substrate can outcompete the inhibitor. Absolutely right. Substrate can outcompete the inhibitor. Now, what would be the consequence on Vmax? Let's think about that. We said Vmax tells us how the enzyme behaves when the substrate concentration is very high. If we have an competitive inhibitor, by the way, that is the C here, IC, that means a competitive inhibitor. How would a competitive inhibitor influence Vmax? The answer is Vmax is not changed. Vmax is not changed if the substrate concentration is incredibly high. So that's Vmax basically. In the presence of a competitive inhibitor. So if we have a competitive inhibitor, it does not do anything to Vmax. Vmax is unchanged. Very good question. Or in other words, let me just finish that. Vmax stays constant with a competitive inhibitor, or a competitive inhibitor does not work if the substrate concentration is very high. These are basically all the same things. Competitive inhibitor does not work if the substrate concentration is very high because the substrate outcompetes the inhibitor. Now, what about Vmax over Km? what happens to this when we have an inhibitor? Vmax over Km tells us how the enzyme behaves at very low substrate concentration. So if we have very little of the substrate here, would we see a strong effect of the inhibitor? Yes or yes? Absolutely, I didn't give you many options. So the competitive inhibitor reduces Vmax over Km or in other words, the competitive inhibitor works best when the substrate concentration, when the substrate concentration is very low. Because there's nothing to compete against. There's hardly any substrate left, so the inhibitor grabs the enzyme and forms this inhibitor complex. So, in the case of a competitive inhibitor, Vmax stays the same. Vmax over Km goes down. It is reduced by the competitive inhibitor. Now, what happens to Km? And Peter really asked this question, and that's a very, very good question. Will it go up, down, or stays the same? What do you think? You're absolutely right. Km has to go up. Km must go up. IC increases Km. It must go up because we can deduce that from the Vmax over Km. Vmax over Km, we said this goes down, but we also know that Vmax stays constant. And it can only, Vmax over Km can go down if, I didn't mean to do that. This can only happen if Km goes up. Only if Km goes up, then Vmax over Km goes down if Vmax stays the same. So Km increases the competitive inhibitor increases Km. So Km must go up in this case. Does that make sense? So these are the properties of the competitive inhibitor. Vmax stays the same. Vmax over Km goes down. Km goes up. How would we see that in a plot? Let's do our Eadie-Hofstee plot. V over S. Let's say that is without the inhibitor, minus IC, and with the inhibitor, we would get something like that, plus competitive inhibitor. We still have here the same Vmax, but what we see here is Vmax over Km goes down. And that is V over S, yes. So that is how we would see our competitive inhibitor in a plot. Right. Now, how does a competitive inhibitor actually work? So what are the mechanisms? And you notice I put it in plural, mechanisms of IC. There are two ways a competitive inhibitor works. And at school, you are only taught one of them. When can a competitive inhibitor sort of compete with the substrate? What do you think? What are the conditions for a competitive inhibitor to compete with the substrate? Lovely. Thank you very much. It binds to the active site. This is an active site inhibitor. So if the inhibitor looks similar to the substrate, then it sort of can pretend. It can pretend to be like the substrate. So the normal substrate would fit here. So that's our substrate here. And the inhibitor might look like that. So that's the competitive inhibitor. And you see, in this case, the inhibitor can bind to the active site, but then it blocks it. And what you also see is that the substrate and the inhibitor are mutually exclusive. If the substrate has bound, the inhibitor can no longer bind, and the other way around. Okay, so that is an active site inhibitor. The second one is called an allosteric inhibitor. Allosteric inhibitor. And that is also a mechanism by which a competitive inhibitor works. So again, we can say, right, we have here, like in this case, we have our substrate, and now in this case, we have another inhibitor that binds here. This is here the allosteric action of a potential allosteric action of a competitive inhibitor. It binds to an allosteric. Allosteric, allos means other, steric means position or something like that. It binds to another position in the enzyme, and as a consequence, the binding site for the substrate is closed. So the substrate here can no longer bind. On the other hand, if we have the substrate bound. If the substrate is bound, then the allosteric inhibitor can no longer bind. So again, you see, mutually exclusive. Either the inhibitor binds, then the substrate cannot bind, or the substrate binds, and then the inhibitor cannot bind. This is the concept of an allosteric This is the concept of a competitive inhibitor, and it can display two different properties. It can be either an active site inhibitor or it can be an allosteric inhibitor. It can't be both at the same time. It depends on, that's a very good question, Daria. It actually depends on how good the inhibitor binds. So, and that brings me to the next subject. Let's have a look at actually what happens. And it's only one. We are talking about a competitive inhibitor, and that is reversible, and they can act on the active site or somewhere else, but they are mutually exclusive. So what we what we can see is basically we can determine which one is better, substrate or inhibitor, which one binds better. So for the enzyme and the substrate, we can write we have an enzyme substrate complex. And in the first part of this Michaelis-Menten equation, we have enzyme plus substrate. Okay? I've written it usually the other way around, but that's very easy to see. And we can say we have concentration of enzyme times concentration of substrate divided by the concentration of the enzyme substrate complex. And that is usually given as the dissociation constant for the substrate. That's the dissociation constant for the substrate. And we can do exactly the same for our inhibitor. We have an inhibitor complex, and we have it like E plus inhibitor. So here we can write E times the inhibitor concentration divided by EIC, the concentration of the inhibitor complex, enzyme inhibitor complex, and this is called KIC, where the I stands for inhibitor and C indicates that this is a competitive inhibitor. Okay? Are you happy with that? The way I've written it. We will need this terminology, KDs, KIC. This is where we have to unlearn. So KIC just means the dissociation constant of the inhibitor. Right. Now, this is our competitive inhibitor. Let's go up quickly. So we said the competitive inhibitor binds exclusively to the free enzyme. You see this here. Okay, let's go for another type of inhibitor. And I know you have been dying to find another kind of inhibitor. What inhibitor am I talking about? Again, if you want to leave a little bit of space, E plus S, we have ES, and we have then product plus enzyme. And we said for the competitive case, we have the binding here. That's the competitive case. That's a competitive inhibitor. Where else could the inhibitor bind? Substrate and product are exempt. Yes, absolutely right. Both of you are right. The inhibitor can bind exclusively to the enzyme substrate complex. Absolutely right. Good thinking. And again, because it's a reversible inhibitor, we have this equilibrium and we form a complex E, S, I. And in this case, I want to indicate that this is a different inhibitor. And I indicate that with a U. ESIU. Let's make the arrow nice here. So you see here, IU can only, and I write that in large letters, can only bind to the ES complex. It cannot bind to the free enzyme. So let me remove this arrow here, because it cannot bind to the free enzyme. It can only bind to the ES complex. So it is basically exactly the opposite of a competitive inhibitor. How would you call the opposite of an competitive inhibitor? It is not mixed. So you call it a non-competitive. I'm afraid this type of inhibitor is called an uncompetitive. It is an uncompetitive inhibitor. Because it's exactly the opposite to a competitive. It does not compete. It does not compete with the substrate. In fact, the uncompetitive inhibitor needs the substrate. Needs binding of the substrate in the first place. So how does that work in terms of mechanism? We have our enzyme, the boy. we have the substrate, and we have an inhibitor. The inhibitor can't do anything with the free enzyme, because this uncompetitive inhibitor cannot bind to the free enzyme. Only when the enzyme has bound the substrate, a new binding site will open. New binding site opens in the enzyme, and this is a new binding site for the inhibitor. And this means that in this case then, maybe I should try to get this drawn like that again. Here we've got our substrate bound. Only when the substrate has bound, our inhibitor can bind again. So that is this enzyme substrate inhibitor complex. That's the ESIU. And when this complex forms, no further reaction happens. So the uncompetitive inhibitor, please park that thought, Hannah. Park that thought. We are not discussing non-competitive inhibitors, at least not today. The uncompetitive inhibitor can only bind when the substrate has bound. It needs the binding. So when is this uncompetitive inhibitor most effective? We said for the competitive inhibitor, let me go back. A competitive inhibitor does not work if the substrate concentration is very high. Now, what is the case for the uncompetitive inhibitor? Does it work when the substrate concentration is very high? Yes, absolutely right. Uncompetitive inhibitors only work if the substrate concentration is very high. It works best when the substrate concentration is very high. When does it not work? They do not work if the substrate concentration is very low. Absolutely right. Only if the substrate concentration is very high, then the uncompetitive inhibitor will work. So in this case, substrate concentration very high, this is indicated by Vmax. And because it is an inhibitor, Vmax will go down in the presence of an uncompetitive inhibitor. Vmax has to go down. It is an effect on the rate. The inhibitor only works, is effective, if the substrate concentration is high. and therefore Vmax goes down. It does not work when the substrate concentration is low. So our Vmax over Km will be not affected because the inhibitor doesn't work then. So for an uncompetitive inhibitor, Vmax goes down, Vmax over Km stays the same. What's the effect on Km? What do you reckon? Up, down, or the same? Edith, we come back to that question next on Friday. Km, in order to give us this picture, Km also has to go down exactly the same way like Vmax, because we said Vmax over Km should stay the same. Vmax goes down, so therefore Km must also go down. So for an uncompetitive inhibitor, we have Vmax goes down, Km goes down, Vmax over Km stays the same. In an Eadie-Hofstee plot, we would find V over S. That is without the inhibitor. And with the inhibitor, they are both here at the same time. With the inhibitor, we get this picture. Here, Vmax over Km stays the same, but they have different Vmax. And you see Vmax goes down in the presence of the inhibitor. So let me just quickly recap. What we have dealt with today were two different kinds of inhibitors. Oh, by the way, where does the uncompetitive inhibitor bind? When we talked about the mechanism, does it bind to the active site or does it bind allosteric? Binds to the enzyme substrate? Absolutely. An uncompetitive inhibitor is always allosteric. It is an allosteric site. So what you see is when you talk about an allosteric inhibitor, it can be an uncompetitive one or it can be a competitive one. So the terminology of an allosteric inhibitor doesn't mean a lot. So what we have discussed today was the competitive inhibitor that is only binding to the free enzyme and is mutually exclusive. Either the substrate or the inhibitor can bind. In contrast to that, the uncompetitive inhibitor, it can only bind to the ES complex once the substrate has bound. And in the session on Friday, we will discuss what happens, what Edith suggested, what happens if you've got both present. And, well, I'm not going to tell you what you will find, but again, no, it is not binding to the substrate. Look at this diagram here. The substrate is here in the active site. Here is the substrate. But the inhibitor binds here to an allosteric site remote from the substrate and from the substrate binding site. And when you form this complex, this reaction here to form the product can no longer proceed. I hope this makes sense. I'm way over the time. I apologize for the glitch at the beginning, but I hope you learned something. And again, take with a pinch of salt what you have been taught at school. No, I'm afraid I don't have any inhibitor jokes. And if I knew, I would just simply be too inhibited to tell you, because really it is a totally competitive world out there. So thank you very much, and have a lovely afternoon. Stop the recording.